Hello students, welcome back. We just completed the main theorem of linear congruence. It's important, so let's review it again briefly. A and C are integers, and D and M are positive integers. While A, C, and M are arbitrary, D is determined as the GCD of A and M. Then we get this conclusion. The linear congruence equation, AX is congruent to C modulo M, has no solution if the GCD does not divide a constant term C. If D divides C, then the equation has D incongruent solutions. Yes, it has infinite many solutions, in entire set of integers, but there are M equivalence classes modulo M under the equivalence relation congruence modulo M, and among those M classes classified by the remainders 0, 1, 2, 3, 4 and all the way up to m-1, only D of them will have solutions. All the elements of those D selected equivalence classes will have solutions, and the others will not. More precisely speaking, we are going to get this form. M over D, that's an integer, times R, where R is running from 0 to D. 0 to D minus 1, to be a bit more precisely speaking. So they are D equivalence classes. So that was the main theorem. And let's discuss how to utilize this. Yes, you can utilize that to some actual examples, but before that, let's discuss this important corollary. In a special case when C is 1, we have this particular case, AX is congruent to 1, so C is 1 this time. In that case, what do you mean by D divides C? The only positive integer that divides 1 is 1, so that's when the GCD is 1. When A and M are relatively prime. In that case, there are D congruent solutions, but these ones, so it has only one congruent class of solution. So solution is unique, modulo M. And that D is not 1, then there's no solution. So you can rewrite like this. There is a solution if and only if A and M are relatively prime. Not only that, you can find how many solutions there are. Actually, there is unique solution, modulo M. There are infinite many integer solutions, that's true, but they're all congruent, modulo M. So there is a unique solution. So that's a special case, and the proof is left to the students because this is basically nothing new except that taking C as 1 and then considering D dividing that 1 is just D equals to 1 and nothing else. So this is a trivial corollary of the main theorem, but as a matter of fact, it's very, very useful. Very useful. Let's consider these example problems. First two look very easy. We have modulo 7, so not many. Second problem, no, not second, third and fourth problems are intimidating. And the right-hand side is 1 and 4, same as before, but modulo 4,620. And also A value is pretty big as well, 101. Okay, how do we work it out? Problem A, well, we can consider two methods. One, brute force method, just try them all. 3 times 0 is 0, no problem there. And then 3 times 1 is 3. No problem there either. Wrong color, I want it gray. And then we can consider all other cases. Yes, you see, First two cases are not that important because they are so obvious. Unless this one is same as A, in which case we get x is congruent to 1 directly. Otherwise, checking 0 and 1, those are useless. And there are only 5 cases to check. There are 7 equivalent classes, yes, but we don't have to check all 7. There are only 5 cases to check. 3 times 2, 3 times 3, 3 times 4, 3 times 5, and 3 times 6. Among these, well, we have the answer here. 3 times 5 is 15, and that's congruent to 1, because 14 is 7 times 2, that's congruent to 0. So we have a solution like that. Here's alternative solution, Bezout's identity, Bezout's linear combination identity. 7 is 2 times 3 plus 1, 6 plus 1, so we can rewrite like this. 1 times 7 minus 2 times 3 is 1. So we have linear combination leading up to the GCD. Now 1 times 7 is 0, 7 is congruent to 0. So drop it out, what do you get? Negative 2 times 3 is 1, but what is negative 2? What is negative 2 modulo 7? Is 7 minus 2? It's 5. So negative 2 is 5. So x is 5 modulo 7. 5 times 3 is 1 modulo 7. The same answer as before, but we use a bit trickier and more clever method. Which is easier? Of course, the brute force method is easier in this case. That's because 7 was such a small number. How about the next problem? Well, you can use the brute force method again. 3 times 0 is 0, but nobody cares. 3 times 1 is 3. Again, that's not very important. There are 5 cases to check. As a matter of fact, there are 4 cases to check because we already did this. Well, in any case, we get 3 times 6 is 4. So we get x is congruent to 6 modulo 7. Just 5 easy computations to check. Now, what if you use Bezout's identity method? Well, you can use the same linear combination to find out the multiplicative inverse of 3, and then multiply 5 to both left-hand side and right-hand side. So 5 times 3 is 1, so we have just x. 5 times 4 is 20. So multiplying 5 to both left-hand side and right-hand side, we get 5 times 4 in the right-hand side, and that's 20, and that's congruent to 6. Remember, 14 is congruent to 0, modulo 7. Again, which method is easier? I don't know about you, but the brute force method appears to be easier, just trying them all. But how about the next problem? 101x times 101x is congruent to 1, modulo 4620. Whoa. How about the brute force method? Good luck about that. Try all 4620 computations. Well, in practice, these two are not very important. So you can try only the rest. 4,618 computations to go. Good luck. What if you use Bezout's identity method? Okay, let's try that. Remember how to do that? We use Euclidean algorithm to find out the GCD first. 4,620 divided by 101, we get the quotient 45 and remainder 75. Now, use the remainder to divide the divisor. 101 is 1 times 75 plus 26. We get a new remainder. Divide 75 by 26. We get quotient 2 and new remainder of 23. Divide 26 by 23. We get quotient 1 and a new remainder of 3. Divide 23 by 3. The divisor by remainder, divisor by remainder, divisor by remainder, that's continuing. So 23 is 7 times 3 plus 2, and then one more. Divisor by remainder. 3 divided by 2, we have quotient 1 and remainder 1, and that's it. Finally, we got 1. So these two numbers, 4620 here, m, and 101, these two are relatively prime. Of course, we knew that already because 101 is a prime number, but still, we had to go through this Euclidean algorithm. That's because we want to find out Bezout's linear combination expression. What we are going to do is to backtrace this Euclidean algorithm. 1 and flip this one over. 3 minus 1 times 2. That comes from the final line. Is that clear to you? Flip it over. Next, 3 versus 2. 2 is smaller. So this 2, we can use the next line here so that 2 is 23 minus 7 times 3. We get this. As highlighted in green. And then simplify. We get 8 times 3, yeah? Negative 1 times negative 7, so positive 8. And then minus 1 times 23, and 3 is smaller. Now we use the next line, which I just highlighted in purple, in place of this 3 right here, right there. So this purple. And then simplify, we get 8 times 26 minus 9 times 23, which is smaller. 23 is smaller, so let's use the next line here as highlighted in brown. So this 23 is replaced by this. 75 minus 2 times 26, and then simplify. Which is smaller? This 26 is smaller, so we use the next line. 26 is 101 minus 1 times 75, so this 26 is replaced by that. And then simplify. Finally, this 75, highlighted in this magenta, so the final line here, 75 is 4620 minus 45 times 101. That's what I replace right here and simplify. What do you have? 1601 times 101 minus 35 times 4620. So that's the linear combination expression that we wanted all along. And then here, this is congruent to 0 modulo 4620. So what do you get? 6001 times 101 is 1, so we get the multiplicative inverse, 1601. So 101 times x is 1, that means x is the multiplicative inverse of 101, 1601. That's how you get the solution. Euclidean algorithm, backtracing the Euclidean algorithm, and then dropping that out because that's 0. And then that'll give me 1601 times 101 is congruent to 1. That's going to be the multiplicative inverse that I'm looking for. Okay, all right. How about the next problem? Well, we found out the multiplicative inverse in the previous problem. So we just multiply that multiplicative inverse 1601 to both left-hand side and right-hand side. And then 1601 times 101 is 1, so x, we get 1601 times 4, well, a bit of a computation yields 1784. So that's my solution. So find out the inverse and then work with the inverse.